Hi folks, Mr. Kozer here. Sorry about the medium quality audio, but I'm going to share with you some ideas about projectiles. So yesterday in class you saw some information with a demonstration about a falling ball that moved similarly to a ball that was projected sideways. And the point about the ball that was projected sideways and the ball that fell vertically is that they were always at the same position vertically, yet the one that moved sideways also gained horizontal position over time. So this one had a horizontal velocity that was constant, but they both had vertical velocities that were increasing. And what I want you to notice about that is that they behave the very same way vertically and differently horizontally. So what you can notice is that for the launched ball, we know it's vertically accelerating and horizontally not accelerating. And for the dropped ball, we know vertically it is accelerating, but horizontally it's also not accelerating. But the difference is that the launched ball has a velocity horizontal, and the dropped ball does not have a horizontal velocity. The important message from this demonstration is that the horizontal and vertical motions of an object are independent of each other. Whether or not something is moving horizontally doesn't affect how it is moving vertically. So I'd like you to use that strategy to try doing some problems using the equation tools that we have used before. So I've grabbed a single problem from the projectile practice problems, which is a horizontal launch problem, and I'd like to help you think about how to deal with it. You'll notice we have our two equations that are familiar up on top. I didn't include the third one that's not including the time because we really won't need it. But the key idea is to think about how you can deal with these problems. Well, let's consider what we're looking at. Here's a rock that's thrown horizontally at 18 meters per second. So that's going to be VIH, H for horizontal. Where is it 1.5 seconds later? That's a time. So if I'm looking for VI horizontal, I have two choices. I either have a distance equation or a velocity equation, and I'm going to choose the velocity one. So I'm looking for VF, so I'm going to write my equation, and I'm going to recognize that everything I'm doing is horizontal. Notice the time doesn't have a horizontal and vertical because that fits both. I'm looking for VFH. I know VIH is 18 meters per second. I know AH is 0 because the ball is not accelerating horizontally, only vertical. And the time I care about is 1.5 seconds. So horizontally, I know the speed. And this just describes that the horizontal speed is always 18 meters per second. Let's think about vertically what's happening to it. VF vertical, VI vertical plus A vertical T. Well, at the beginning, it starts off only with the horizontal speed, not with the vertical. So the final vertical velocity is 0. It's beginning vertical velocity plus A vertical, that's gravitation, times time, which is 1.5 seconds. So if we were curious to know about what's happening to the velocity, we see that this, assuming G is 10, tells us that the ball will be moving 15 meters per second down and 18 meters per second, presumably to the right, at time of 1.5 seconds. So you'll notice that equation allows us to decide how fast something is moving, but I dealt with horizontal motion and vertical motion entirely separate from each other. Now, the question doesn't ask for that. The question asks for where it is. So let's try using the position equation and do the same thing. I'm going to grab a fresh page and continue. To answer the question, where is the rock, what I really want to use is the distance equation. So I'm going to do the same thing, distance, distance, and I'm going to write out the whole equation, but I'm going to recognize that I'm going to deal with it horizontally now because that's my question, at least for now. So to find the horizontal distance, I'm going to call the initial position 0, 0, so I'll call this the initial horizontal and the initial vertical, 0, 0. The initial horizontal speed we know is 18 meters per second. The time we care about is 1.5 seconds. And horizontally, I know the horizontal acceleration is 0. So this entire last term is not helpful because it disappears. So what I'm really left with is that horizontally, where is it? Well, that's 18 times 1.5. That's 27 meters away. There's my horizontal position after a second and a half. Let's do the same thing, but let's do it for the vertical position. So they're at the exact same equation. And now I'm going to do the same thing, but consider only the vertical information. And now we're going to try it again. The vertical, VI vertical, 0. VI vertical, well, this initial speed is VI horizontal. It has no VI vertical speed, so that's 0. 1.5 seconds is the time. And then the third term is 1/2 times g, because that's the vertical acceleration, times 1.5 seconds squared. Now in this case, you'll notice that the first term is 0, the second term is 0, and only the third term gives us a useful value. So dFv, again, I'm going to use g as 10, so 1/2 of g is going to be 5. So then I'm going to grab my calculator, and I'm going to check out 5 times 1.5 squared, and that gives me 11.25 meters. So what I know is my final position, 1.5 seconds later, is going to be 27 meters sideways and 11.25 meters down from my original position. So again, by totally separating the horizontal motion from the vertical motion, I was able to identify where the object goes.